Welcome to the second chapter of this course. This is the first part. Here I will cover motion and kinematics. The topics covered here are vast and we will only be able to scratch the surface, but it should give you a good taste for how scientists study physical systems. As the circle moves to the right, images of the object are left behind, indicating where the object was located. The number is the frame number. The image formed displaying the object's location at each frame is called a motion diagram. The time interval between frames in a motion diagram is always equal. So, for example, in the motion diagram above, each frame is separated by approximately 1 second. In uniform motion, adjacent frames are equidistant. You can see that in the image above. In uniform motion, the motion moves with constant speed. You can see that the circle is moving to the right at a constant rate. Objects with a changing speed are accelerated. Objects that accelerate in the same direction as their motion increase their speed, and that is shown with the green circle above. The double arrows show you the space between frames. Remember, each frame has the same time interval. Between frames 1 and 2, there is a relatively short distance. From 2 to 3, that distance gets longer. That means that the green circle traveled further within the same amount of time. Or in other words, it was moving faster, meaning it was accelerated. You can see that with each subsequent frame, the distance between frames gets even longer. Objects that accelerate in the opposite direction as their motion decrease their speed, and that is shown with the pink circle. You can see that the distance between frames gets shorter. For example, from 1 to 2, it's very long, but from 2 to 3, it's much shorter, and from 5 to 6, it's even shorter. 6 to 7 would be on top of each other because the pink circle has come to a stop. Here are the motion diagrams of 6 objects. Your task is to pause the video and then verbally describe each motion diagram. I will review the answers on the next slide. Let's now review the 6 motion diagrams. The green circle travels a greater distance with each frame, and so it must be increasing its speed. This is accelerated motion, with the acceleration in the same direction as the motion. The distance between frames of the blue circle gradually get closer together. This is accelerated motion, with the acceleration in the opposite direction as the motion. The distance that the brown circle travels between frames is always the same, so it is traveling at constant speed, and it is undergoing uniform motion. In contrast to the previous circles, the gold circle is traveling to the left. The distance between frames always increases, and so it is speeding up. This is accelerated motion, with the acceleration in the same direction as the motion. The purple circle starts closer to the center than the previous circles. Its second and third frames are to the right, with decreasing distance. The fourth and fifth and sixth frames are to the left, and the distance between those frames increases. This object is constantly accelerating to the left, but its initial motion is to the right. At approximately frame 3, the direction of motion changes, and the circle moves to the left. The light blue circle is accelerated in the same direction as its motion, from frames 1 to 4. We know that because the distance between frames increases. After frame 4, the distance between frames remains constant, and so it undergoes uniform motion. This object accelerated in the beginning, got up to speed, and then traveled at that speed. Let's now discuss the topic of coordinate systems. We would like to place numbers on the locations of objects. To do this, we need a coordinate system. To pick a coordinate system, you need to do these things. First, pick the location of 0, then pick which direction is positive, and then give the coordinate a label. We are free to pick any coordinate system we want, but it is recommended to select a coordinate system that makes the mathematics easier. Changing a coordinate system doesn't change the physics, so changing a coordinate system shouldn't change the results. Here are some common coordinate systems. Make the horizontal the x-axis, where displacement to the right is positive. Make the vertical the y-axis, where displacement upward is positive. Make rotations that are from the positive x-axis to the positive y-axis positive, and label them theta. Moving forward in time is positive. And set the origin xy equals 0, 0 and t equals 0 where and when an object starts its motion. Here is the motion diagram of the object undergoing uniform motion from earlier. In this motion diagram, we have chosen the x-axis as the axis of motion, and we have taken motion to the right as being positive. The object starts at frame 1, so it would be natural to take x equals 0 and t equals 0 at frame 1. There is only horizontal motion, so there is no need for a y and z axis or a rotation axis. Position of the object is its x-coordinate value. Distance is the length of the space between points. Distance traveled is the length of the path traveled. Distance and length are by definition always non-negative values. We can go ahead and write the position of each frame like this, where d is the distance between frames. We were not obligated to select frame 1 as the origin and start time. We are free to pick a different one. The selection of the origin is arbitrary and can be set to another frame. Here is the origin set to frame equal 4. The distance the object travels between frames doesn't change with a changing coordinate system. Here is the position of the object at each frame, updated with this new coordinate system. Here, the position values have been updated with a change in coordinate system, but the distance between frames is still the same. Let's now discuss the delta operator. Delta is a Greek letter, and here we are using the capital version of the delta letter. Appending a delta sign in front of a variable means a change in that variable, not just the variable itself. So for example, delta x means change in x. Delta t means change in t. And delta v means change in v. These variables have a starting and ending value. Starting values will often have a subscript of 0, I, or 1. So for example, x sub I, t sub 1, or v sub 0. For variables that have a subscript of 0, often people will say not, so you would say v naught. Ending values will have a subscript of f or a higher number like 1 or 2, or sometimes no subscript at all. So for example, x sub f, t sub 2, or just v. The selection of subscript changes with author and the context. Delta subtraction is always the final value minus the initial value. It is never the other way around, and it is a common mistake for students to get the order of subtraction backwards. So, for example, delta x means x sub f minus x sub I. Delta t would be t sub 2 minus t sub 1. Or delta v would be v minus v naught. Now that we have discussed position and coordinate systems, we can discuss displacement, velocity, and speed. Position is the location of an object within a given coordinate system. Displacement is the change in position. Both of these quantities can be positive or negative or zero. If x represents the position, then delta x represents the displacement. Distance is the length of the displacement, or length of the path traveled. This value can be positive or zero, but it cannot be negative. Velocity is the rate of change in position with respect to the given coordinate system. V equals delta x divided by delta t. Speed is the magnitude or absolute value of velocity. Average speed is the path length divided by the travel time. Quantities that are average will often have a bar above them to indicate average. So average velocity equals distance divided by the time interval. Velocity has orientation and is represented as an arrow, and speed is represented in the length of that arrow. Arrows used to represent physical quantities with orientation are called vectors. Here are 4 velocity vectors. Velocity vectors 1, 2, and 4 all have the same length, and so therefore have the same speed, but each of them are traveling in a different direction. Velocity vectors 1 and 3 are moving in the same direction, which is to the right. However, velocity vector 3 is much longer, and so therefore has a higher speed than velocity vector 1. Velocity vector 2 is moving to the left, and so we say it is moving in the opposite direction as velocity vector 1. Velocity vector 4 is moving upward at a 45-degree angle. Let's now discuss the graphical form of vector arithmetic. Here are 2 vectors, a and b, where a is significantly longer than vector b. Vector a is pointing upward at approximately 30 degrees, and vector b is pointing downward at approximately 20 degrees. The first operation is called vector scaling. This is where we can change the length of a vector or flip it so that it points in the exact opposite direction. Here are some examples. This is negative a. You can see that the length of the vector is exactly the same as that of a. However, it is pointing in exactly the opposite direction. This is 2b. It is pointing in the same direction as b. However, the length is twice as long. If this was 1/2 b, it would be shrunk to be half the length of b. The next operation is vector addition. To add vectors graphically, you take the 2 vectors and connect them head to tail, like this. This is what vector addition looks like. Then we just connect the starting and ending point, so the resultant sum looks like this. The next operation is vector subtraction, and it is done in a similar way. However, the vector that is subtracted is first multiplied by -1, and then we perform the addition of the first vector plus the opposite of the second vector, and it looks like this. That is what vector subtraction looks like. The next topic is acceleration. We saw that displacement is a change in position. Velocity is the rate of change in position. Acceleration is the next step, and it is the rate in change in velocity. It is defined like this, where a is the acceleration equals delta v divided by delta t. Here is a motion diagram of an object that is accelerated to the right. In frame 1, the object has no speed, and so it does not have a velocity vector. However, it does have acceleration, which is represented by the red arrow pointing to the right. In the beginning, it has no motion, and then because it is accelerated, its velocity increases. And with each frame, the velocity vector gets longer, indicating that its speed is increasing. Here is another motion diagram of an object that is accelerated. However, it is accelerated in the opposite direction that its velocity is. In frame 1, the object has an initial velocity that is pointing to the right. However, something is causing the object to accelerate to the left. This causes the velocity to decrease, and so its speed gets smaller and smaller. By frame 6, the speed is 0, and it comes to a stop. Instead of motion diagrams, plots are often used to quantitatively display the motion of an object. Time is put onto the horizontal axis, and the position is placed on the vertical axis. This plot includes two data sets. The blue line is for an object undergoing uniform motion, and the orange curve is for an object undergoing accelerated motion. In uniform motion, the change in displacement is the same for each time interval, and this yields a line. With acceleration, the displacement continuously increases. This type of curve is quadratic and is called a parabola. It is not exponential. Exponential curves are fairly rare in nature, and when they do exist, they do so in very narrow and limited circumstances. The curves on this chart represent the motion of the 6 objects in the previous example on motion diagrams. Take a moment to pause the lecture here and see that each curve describes the motion of an object in the example problem. Note that the color of the curve matches the color of the object. Let's look at the distinction between average and instantaneous velocity. Instantaneous velocity, given the symbol v, is the exact velocity at an instant in time, and is computed from the slope of the position versus time graph. Average velocity, which is given the symbol v with a bar above it, is the average taken over time, and is computed from the ratio of the change in displacement and the time interval. So the average velocity is delta x divided by delta t. In practice, we measure average velocity over a very short time interval. When the velocity or speed is measured over a very short time interval, it is the case that the instantaneous velocity will be approximately equal to the average velocity over that time interval. We would now like to derive the kinematic equations for systems with constant acceleration. We will start with the definition of acceleration. That is, a equals v minus v naught divided by delta t. We would then like to take this equation and solve for v. We will do this by multiplying by delta t on both sides and then adding v naught. And we get this, v equals v naught plus a delta t. We can then take this equation and plot the velocity as a function of time. And it looks like this. This is a line where the y-intercept is v naught, and the slope of this line is a, the acceleration. We would like to take one narrow time segment, and we would like to find the displacement over this time. We know that the velocity is approximately constant over that time. We can then find the area of that rectangle. The area of a rectangle is the width multiplied by the height. The height of this rectangle is the velocity at that time, v, and the width is the time interval, delta t. It's important to note that delta t here is a small time interval. It is not a long time interval. We can then recall the definition of velocity. Velocity equals the change in position divided by the change in time. And then we get that the change in position equals the velocity multiplied by the change in time. We can see that the change in position will be the area of that rectangle. To get the total change in position over the entire time interval, we need to get the total area under the line. The line does not form a rectangle though, it forms a parallelogram. So we must use our equations from geometry to find the area of the parallelogram. The area of a parallelogram is equal to the average height multiplied by the length of the base. Here, the height will be determined by the velocity at both ends, and the base is just the time interval. The area is the total change in position. And so we get that the change in position equals the average velocity, which is 1/2 v naught plus v, and that multiplied by the time interval. We can just clean up this expression and then include the equation for velocity that we found earlier. And we get that x equals x naught plus v naught delta t plus 1/2 a delta t squared. We can then combine this equation with the first equation where we remove time. And when we do that, we get this equation, v squared equals v naught squared plus 2a delta x. And those are the kinematic equations. This is the first kinematic equation, and it relates velocity and acceleration over time. This is the second kinematic equation. It relates initial and final velocity to displacement over time. This is the third kinematic equation, and it gives the position as a function of time. And this is the last kinematic equation. This one is different from the first three in that it is the only one that does not involve time. This is useful in problems that relate velocity, acceleration, and displacement, but do not involve time. Let's do an example of computing the average and instantaneous velocity of a moving object. An object is undergoing one-dimensional motion that can be described by this equation. X of t equals 1.2 meters plus 3.1 meters per second times t plus 0.2 meters per second squared times t squared, where x is the position and t is the time. What is the average velocity from t equals 5 seconds to t equals 6 seconds? And then what is the instantaneous velocity at t equals 5.0, 5.5, and 6.0 seconds? Let's start by calculating the average velocity. To calculate the average velocity, we need to calculate the displacement. So we need to find the position at t equals 5 and t equals 6 seconds. Plugging in t equals 5 seconds, we get that x equals 21.7 meters. And then plugging in t equals 6 seconds, we get 27 meters. The displacement is the difference in these, and we get 5.3 meters. The time interval is 6 minus 5 seconds, which is equal to 1 second. And so the average velocity is 5.3 meters per second. The instantaneous velocity is computed by just evaluating the time at those 3 points from the velocity equation. So first we need to get the velocity equation. We can get this from the kinematic equations on the previous slide. And that is the velocity is the initial velocity plus the acceleration times time. And so that boils down to v of t equals 3.1 meters per second plus 0.4 meters per second squared times t. The 0.4 meters per second squared is equal to 2 times 0.2 meters per second squared because of the factor of 1/2. Plugging in t equals 5 seconds, we get that the velocity at 5 seconds is 5.1 meters per second. Then plugging in 5.5 seconds, we get the velocity at 5.5 seconds is equal to 5.3 meters per second. And then plugging in t equals 6 seconds, we get that the velocity is 5.5 meters per second. So you can see that the instantaneous velocity from t equals 5 to 6 does vary, but that the instantaneous velocity at the middle is equal to the average over that time interval. After acceleration is jerk. We saw that displacement is a change in position, and velocity is the rate of change in position. Acceleration is the rate in change in velocity. The next step is jerk, where jerk is the rate of change in acceleration, and it is defined like this: J equals delta A divided by delta T. Jerk is not usually considered in introductory physics, but is an important quantity for engineers to consider when designing vehicles, and so I wanted to mention it here just for completeness. Large jerk values are uncomfortable or dangerous for passengers of a vehicle, or will increase wear and tear on the vehicle and its track. For example, in an elevator, 2 meter per second cube jerk would be acceptable, but 6 would be very unacceptable. Here are the kinematic equations that have been modified for acceleration that changes over time with constant jerk. Now that we have the kinematic equations, we can discuss free fall and projectile motion. Massive bodies generate gravity, which has the effect of pulling items together. One massive body is the Earth. Near the surface of the Earth, items are pulled downward at an acceleration of 9.81 meters per second squared, or 32.2 feet per second squared. This quantity, which you should memorize, is given the symbol g, and is called the acceleration due to gravity. Items that fall to the Earth's surface under the influence of gravity only are said to be in free fall. Projectile motion is free fall in the vertical axis and uniform motion in the horizontal axis. Remember, uniform motion is motion with zero acceleration. In 2D problems, a subscript x is used on velocity and acceleration symbols for the horizontal axis, and a subscript y is used for the vertical axis. When working kinematic equations on the vertical axis, if up is taken to be positive, then the acceleration on the y-axis is negative g. We'll do an example of projectile motion on the next slide. Let's do an example problem of a horizontal projectile. A ball is rolled down an incline and launched horizontally. The horizontal range, r, of the projectile is measured, and the launch site is a distance h off the ground. What is the launch speed, v0, of the projectile, and what is the time of flight, t sub f? Here are the steps for solving not just this physical problem, but most physical problems. You will almost always want to start by drawing a diagram. Then pick a coordinate system and list your knowns and unknowns. Identify the relevant equations, then use those to solve for the things that you're looking for. Here's a diagram of a ball at the top of the ramp. It moves down the ramp. Here's launched until it hits the ground. Here's a coordinate system, which I will call coordinate system A. In this problem, we will work with several coordinate systems, just to show that we can get the same answers using multiple coordinate systems. Coordinate system A has the origin at the launch site, upward is positive, and motion to the right is positive. Because the ball is launched at this point, its initial velocity vector is v0 pointing to the right. A second coordinate system, B, will have its origin at the landing site. Upward will also be positive, but this time motion to the left is positive, and so motion to the right is negative. And then the last coordinate system we'll look at is coordinate system C, where its origin is below the launch site on the ground. Motion to the right is also positive, but this time motion that is downward will be taken to be positive, not negative. The vertical distance is h. The horizontal distance is r. The acceleration due to gravity pulls downward. And here are our knowns. We know the starting and ending locations, we know h, we know r, we know g, we know that the horizontal acceleration is 0, we know that the vertical acceleration is g and downward, we know that the initial y component of the velocity is 0, and we know that the initial x component of the velocity is v0 and it's pointing to the right. We do not know v0, which is the launch speed. We do not know the time of flight. We also do not know the final velocity. But fortunately for us, we don't need to find the final velocity in this particular problem. My personal choice will be to define all of the symbols as being positive quantities. So h, r, g, v0, and tf are all positive values. If any of them happen to need to be negative, I will explicitly put in a negative sign. You should note that some authors don't make this convention. Some authors, for example, may take h to be a negative value. Let's go ahead and solve this problem. We should start by including a diagram that was shown on the previous slide, and then we should note that the time interval is equal to the time of flight. We now need to find the initial position, the final position, the initial velocity, and the acceleration of the ball in each of the three coordinate systems. Let's go ahead and do that now. In coordinate system A, which is the launch site, x equals 0 and y equals 0. That was the purpose of selecting A. In coordinate system B, which has its origin at the landing site, the ball starts a distance h to the left of the origin. In coordinate system B, motion to the left is taken to be positive, and so therefore its x-coordinate is positive r. The object also starts a distance h above the origin, and in coordinate system B, upward is positive. And so therefore the y-coordinate of the initial position, according to coordinate system B, is positive h. Doing something similar for coordinate system C, we get that the initial position is x equals 0 and y equals negative h. The reason it is negative h is because in coordinate system C, downward is taken to be positive. The object is above the origin, and so therefore its y-coordinate is negative. We can also find the final position. In coordinate system A, the ball lands a distance r to the right. Motion to the right is positive, and so therefore its x-coordinate is positive r. In coordinate system A, up is positive and down is negative. The ball lands a distance h below the origin, and so therefore its y-coordinate is negative h. Coordinate system B is the landing site, and so therefore x and y are both 0. You can do something similar to get the final position according to coordinate system C is r0. This is because the ball lands a distance r to the right of the origin. Motion to the right is positive, and so therefore x equals positive r, and y equals 0 at this point. We can then find the initial velocity vector according to each of the three coordinate systems. In coordinate system A, motion to the right is positive, and all of the motion is to the right on the horizontal axis. Therefore, the x-coordinate of the velocity is all of the speed, v0, and it must be positive. There is no vertical component to the velocity for all three of these, so v sub y0 will be 0 for all three of them. In coordinate system B, motion to the left is positive, but motion to the right is negative. So therefore, the velocity must be negative v0. In coordinate system C, motion to the right is positive, just like in A, and so therefore, the velocity will be v0. We can now find the acceleration according to each of the three coordinate systems. In all three of them, there is nothing pushing or pulling the ball on the horizontal axis, and so therefore the acceleration on the horizontal axis will always be 0. On the vertical axis, the acceleration is g downward. We just need to identify if it's positive or negative according to the coordinate system. In coordinate system A, upward is positive and downward is negative, and so therefore the acceleration is negative g, which is the same in coordinate system B. In coordinate system C, down is taken to be positive, and so therefore the acceleration is positive g. Now that we have all of the parameters for each of the three coordinate systems, we can then plug in the parameters to the equations that are relevant. We have information about time, and we know the initial and final position, the velocity, and the acceleration. So the equations that relate the position over time are going to be useful. Here are the equations you see here in the last two columns. All we have to do now is plug in the values for each row into those equations. For the first one, we get this. YF is negative h, y sub I is 0, v sub y0 is 0, and a sub y is negative g. We can then do that for the other two coordinate systems. We get this and this. And you can see that each one is a little bit different, but you can see how they're also very similar. We can then take each of those three equations and solve for t sub f, the time of flight. And for all three of them, you will get this result, that the time of flight is equal to the square root of 2h divided by g. This shows you that it doesn't matter which coordinate system you use. You can use any coordinate system that you want, and so long as you do the math correctly, you will get the same answer. We can then do the same thing on the horizontal axis, as shown here, and then use this to find the launch speed, which we get is r divided by the time of flight. Again, this shows you that it doesn't matter which coordinate system you pick. You can pick any coordinate system you want. If you do the math correctly, you will get the correct result in the end. Take a moment to review this and see that everything works out correctly. Let's now analyze uniform circular motion. In the animation below, an object is undergoing uniform circular motion, and by that we mean that it is moving at constant speed. The green vector attached to the object is the velocity vector, and you can see that its length never changes, meaning that its speed is constant. However, you can see that the velocity vector is constantly changing directions, and so therefore there must be an acceleration that is responsible for that change, but that does not change the length. That's what we would like to do next. Here are two frames, 1 and 2, of the object undergoing uniform circular motion, and shown are the two velocity vectors, v sub I and v sub f. We know that the acceleration vector is proportional to the difference in velocity vector, so we can do that graphically. From that analysis, we can see that the acceleration vector that is responsible for that type of motion points to the center of the circle. The acceleration that keeps the object in orbit is center-seeking. It always points to the center of the circle. This is called centripetal acceleration. This acceleration only changes the direction of the object's velocity, and not its speed. We would now like to do an analysis to find the magnitude of that acceleration. To do this, we will use an analysis of similar triangles. Here is a wedge. The wedge in orange is approximately triangular. The two legs are the radius of the circle, and the other edge is the displacement, delta s, which is extended by an angle, delta theta. The green triangle is the triangle formed from the velocity vectors. The two long edges are the length of the velocity vector at frame 1 and frame 2, and between them is the difference in velocity, extended by an angle, delta theta. Delta theta is the same in both triangles, so we can solve for it. From the orange wedge, you get that delta theta is delta s divided by r. We get this from the relationship that the arc length equals r times theta. Then the same angle can be found in the green triangle, and that is delta v divided by v. We know that acceleration is the change in velocity divided by the time interval. We can then take that first equation and solve for the change in velocity and plug that into this definition of acceleration. And from that, we get that the acceleration is the speed multiplied by the arc length divided by r multiplied by the time interval. We know that the delta s divided by delta t is equal to v, the speed. Plugging that in, we get that the acceleration is v squared divided by r. Because this acceleration is centripetal, we often put a subscript c to indicate centripetal acceleration. The centripetal acceleration is the speed squared divided by the radius, and always points to the center of the circle. Let's now look at Kepler's first and second laws of planetary motion. Kepler's first law of planetary motion says that planets orbit a star in elliptical orbits, with the star at one of its focal points. This is a circle. A circle is defined as the set of all points that are equidistant from the center. The distance from the center to the point is the radius r, where twice r, which is the diameter, is a constant. An ellipse is very similar to this, and it looks like this. An ellipse is defined such that all points where the summation of the distance from the two focal points is constant. Here, d1 is the distance from the first focal point to a point on the ellipse, and d2 is the distance from that point to the other focal point. The summation of those two distances must be constant. You can see that if those two points, those two focal points, merge together into the center point, you will get a circle. So an ellipse is a stretched out circle. Kepler's second law says that the rate at which planets sweep out an area is constant. A lot of times people will say equal areas for equal time. Here is a planet shown as a green dot undergoing an elliptical orbit around a star. The star is shown as an orange dot. In purple is the area swept out by the planet undergoing that amount of time. And here are three segments. Each of these three segments have a different shape, but they all have the same area. Because they all have the same area, the amount of time it takes for the planet to sweep out that area will be the same. And that is Kepler's second law. Let's now look at planet eccentricity and Kepler's third law of planetary motion. Eccentricity is a measure of how circular an ellipse is. It varies from 0 to 1. A perfect circle will have an eccentricity of exactly 0. And ellipses will have larger eccentricities, with the most extreme case approaching 1. The planet's orbits are mostly circular, and you can see that with their eccentricity values being very small, particularly when compared to the ellipses on the previous slide, which have eccentricities of around 0.8. In this table, the eccentricities for each of the planets is listed, and the most elliptical orbit is that of Mercury. You can see that the planets, although they technically orbit in elliptical orbits, are only slightly elliptical. They are mostly circular. Kepler's third law of planetary motion says that the square of the period of orbit is proportional to the cube of the mean radius. Or in other words, t squared is proportional to r cubed, where the proportionality constant depends on the mass of the sun. Here is the data of the period plotted against the mean distance from the sun for the various planets in our solar system, plotted on a log-log plot. A log-log plot is different from a linear-linear plot in that each major division is 10 times the previous division, whereas in a linear plot, each major division would be equally spaced. The horizontal axis, which is measured in gigameters, has major divisions of 10, 100, 1000, and finally 10,000 gigameters. The vertical axis is similar, but measured in gigaseconds. Because this data forms a line on a log-log plot, the slope of this line will tell us the ratio of the powers of the variables, which in this case is 3/2, or 1.5. That concludes today's lecture on motion kinematics. Let's go ahead and review the key lessons. First, we looked at the various types of motion. There is uniform motion, which is motion without any acceleration, and then an object moves at constant speed. There is accelerated motion, where an object will speed up or slow down or change directions. Free fall is an object that falls under the influence of gravity, and the acceleration due to gravity is 9.8 meters per second squared. Projectile motion is an object undergoing free fall with an added horizontal component. There is uniform circular motion, where a centripetal acceleration pulls an object to cause it to rotate around in a circle with constant speed. And we looked at Kepler's laws of planetary motion. We also were able to describe motion. First, we looked at the definitions of position, displacement, and distance, as well as velocity and speed, as well as the distinction between average and instantaneous. Then we looked at acceleration and jerk. We looked at coordinate systems, and we saw that we can pick any coordinate system that is convenient for us, so long as we do the math correctly. We did examples of graphical vector arithmetic. And we looked at the kinematic equations, where we're able to find the state of an object